Okay, our next speaker is uh, Professor Brian Zhou from Boston College. Please join me in welcoming Professor Zhou.
Okay, thanks everyone. I'd like to thank Yonglong and the organizers for inviting me here to this really nice conference. I think I'm coming from a community that's trying to get into the game of strongly correlated materials. So I represent the quantum sensing community, and I hope as the years pass, we'll have more and more relevant results to present. But today I just want to give an overview of sort of what our tools can do and also some initial progress in quantum sensing of quantum materials. Okay, so we had really quite a number of talks, both in theory and experiment, detailing the fantastic physics that has come from being able to really design materials at the atomic scale. So to take apart materials layer by layer and to reassemble them, sometimes with a twist. And this has been given the analogy of Legos or maybe a deck of cards. But actually, if you're like me, when I wasn't familiar with the field, the samples are really small. So they're not really a deck of cards or Legos unless you shrink yourself down 1,000 times. Of course, this is no problem for electrical measurements because of the sheer power of nanolithography. So just a single electron, across several micron can produce a potential that's, if unshielded, can produce a potential of millivolts. So we can measure these quantities with electrical transport without any trouble. But electrical transport provides limited spatial resolution. On the other hand, there's a whole host of other techniques, such as scattering-based techniques, where actually you're challenged by sensitivity quite a bit. So neutron scattering, Lorentz transmission electron microscopy, where you're relying on the interaction of the beam through a thickness of the sample, cannot really access the same van der Waals materials. And you see some of these other probes are some of our best probes for bulk magnetism. So these are two challenges that actually conveniently can be addressed by other advances in atomic scale engineering, most notably the recent creation of single defect centers in the solid state. So for example, the nitrogen vacancy center in diamond is a substitutional nitrogen next to a vacancy center, and we can isolate the fluorescence of single NV centers in the lattice, as well as now there are single carbon defects that you can isolate in hexagonal boron nitride. And what's great about these single spin defects is that actually you can get very close to materials because they are trapped in the solid state. So for example, you can fabricate diamond scanning probe tips. This is from the group of Patrick Malakinsky in Basel, or you can just put materials on top of diamond where you have these sensors right underneath within nanoscale proximity. And even in these van der Waals heterostructures, if you have defects in HBN is already part of your heterostructure. They can provide a sort of an embedded reporter of the material properties. So actually, you can buy these tips actually commercially from these companies in Switzerland right now. So we buy our tips from Q Zaber. So yeah, my group at Boston College works on basically exploring applications of NV centers in diamond to questions in condensed matter. So we're trying to develop state-of-the-art instrument resolution in magnetic field sensitivity and spatial resolution. And we really want to answer sort of what questions quantum sensing can solve, both giving perspectives that's additional to conventional techniques and also alongside conventional techniques by looking at the correlation between quantum sensing measurements and say electrical transport or optical measurements. Okay, so here's a picture of our department and some facilities at my lab. So in particular, I have this scanning NV setup from AdaCube. I was actually one of the first to buy this in 2018. So it goes down to 2 Kelvin and it has a 111 vector magnet. So some of the topics I've explored in my group are light matter interactions in materials, so imaging photocurrent flow and optical control of magnetism. And we do a lot of work on the physics of 2D magnets, which I'll weave in to my talk today as I present the capabilities of our technique. Okay, so the beauty of the NV center in diamond is that the spin of the NV center can be read out through fluorescence. So the NV center consists of a ground state spin triplet and an excited state triplet within the band gap of diamond. So it's a deep defect. And what you do is you can shine green laser light on the NV center and it will emit red laser light. So phonon downshifted spectrum. So the trick is that actually the m sub s equals plus or minus 1 states in the excited state actually couple to the intersystem crossing that actually decays non-radiatively, or at least not within your wavelength of collection. So if the electron gets cycled up to the excited state and then it gets stuck in this intersystem crossing, which is a very slow process, you will get fewer photons out than if the electrons were in the m sub s equals 0 state. So this allows a phenomenon of optically detected magnetic resonance where I can read the ground state spin of the NV center out just by how bright or dark the spin is under excitation. Okay, so the typical experimental setup looks something like this. It's a confocal microscope where I can focus laser light down to a micrometer spot and raster it on the sample. The NV centers are actually, the samples we use, if it's a bulk sample, they're actually really, really pure, so part per billion defects, such that the spacing between 2 defect centers is bigger than the optical spot size. So if we shine our laser at one of these spots and then drive a microwave between the ground state transitions, every time we hit a magnetic resonance, the spin gets driven to the m sub s equals plus or minus 1, and we see less fluorescence coming out from the sample. So the splitting between these two states gives us the material's stray magnetic field. What's the sensitivity? Yeah, the DC field sensitivity for our technique is about microhertz per root Tesla. So we can read out about single-digit microhertz in 1 second. Yeah, that sensitivity is determined by the amount of photons you get out and how sharp these lines are. Okay, so if we scan the magnetic field here, you actually see the Zeeman splitting of the NV center. There are two extra peaks here, and that comes from this data comes from an ensemble sample. You see that the NV center actually has 4 different orientations in the diamond lattice along the 111 directions. So 3 of the orientations are degenerate in this picture, and one of them is splitting linearly. Okay, so actually I kind of sold the NV center short. It's actually more than just a magnetic field sensor. So the full Hamiltonian actually depends on a whole number of things, including temperature, axial and transverse strain, and as well as electric fields. So this has motivated a tremendous number of applications from nanothermometry, nanothermometry, orientation sensing. You see there's a dot product on the magnetic field. So if you have a static field and then you change the orientation of the NV center, you can pick that out from the resonances. as well as imaging ferroelectric domains in yttrium manganese oxide and current flow in circuits, and even to detect weakly interacting massive particles that go through maybe a diamond detector, although you would need to image the strain as it moves, as it kicks out atoms from a diamond detector. So you would need a lot of diamond for this to have any cross section, but it's at least been proposed. Okay, so but what can quantum sensing reveal about materials? So today I'll go over sort of two main applications. One is in the spatial domain, which is imaging sort of magnetization and current flow through the Ørsted field at sub 50 nanometer resolution. And one is to measure essentially fluctuations or noise in the temporal domain. So, but you can also combine all of these modalities with material excitation. For example, you can drive spin waves in a magnon. You can drive spin waves in a ferromagnetic insulator. You can also drive photocurrents, and then you can also excite the material with AC magnetic fields to measure AC susceptibility, as we did in our lab. Okay, so how do we go from measuring a stray field to a magnetization? Well, the stray field just comes from an integration of the magnetization over the sample surface. So that's just given by the dipole moment, and it's a convolution over the sample volume. So these convolutions can be handled in Fourier space, where if I measure the stray magnetic field, the Fourier components of that stray magnetic field is directly related to the Fourier components of the magnetization. However, you'll note that actually this matrix that relates the magnetic field in Fourier space to the magnetization in Fourier space is not actually, the rows of this matrix are linearly dependent, and it's not actually invertible. So you'll see that the second row is just the first row multiplied by ky over kx. So this means actually we can go from magnetization to magnetic field, but we can't go backwards uniquely without assumptions. Okay, so you'll also note that there's an effective weighting function, this 1 over alpha plus times 1 over alpha times k, that modifies the magnetic field. So it really means that the NV center is most sensitive to spatial frequencies at the spatial frequencies of order 1 over z, where z is the distance from the sample. So if you're 50 nanometers away from the sample, you're not really going to sense uniform magnetizations that are much longer than that, just because at the inside of a ferromagnet, actually the magnetization is actually 0. The magnetization is highest on the edges of the ferromagnet. And then you're also not going to sense Fourier components that oscillate much faster than how far you are from the sample. Okay, but people can apply assumptions and reconstruct the magnetization. So this was most famously done for 2D chromium iodide by Patrick's group, where chromium triiodide is a A-type antiferromagnet. So even layers should have compensated magnetizations, and odd layers should have a single uncompensated magnetization. So here you see a 2-layer, 3-layer sample, and you only see magnetic field from the 3-layer sections. And using this inverse, by assuming that the magnetization is in the z direction, you can get the quantitative magnetization density. Okay, so we did this actually recently. We've worked with another 2D antiferromagnet, chromium thiophosphate, CrPS4, and this is our data on a 5-layer section. And actually here we can reconstruct the magnetization, but the magnetization actually is not purely along the z-axis or the AB axis. It's actually tilted, and we do this magnetization by trying to get the most uniform magnetization over the area of the flake. So if you actually assume a purely z outer plane magnetization, your reconstruction leads to the reconstruction will show spurious gradients, whereas the magnetization at the optimal angle of the magnetization gives you actually a very uniform magnetization over the flake. But you may notice that actually there's a little bit of reconstructed magnetization sort of outside the flake, and that's not noise. It's actually coming from the even layer regions. So here is a sample that has between 1 to 4 layers, and we see that the 3-layer regions are in opposite states. So down, up, down for the blue, and then up, up, down, up for the red. But this sample is connected, so it means there's a domain wall. There's a domain wall somewhere. So can we see that domain wall? And actually, the domain walls cuts right across the bilayer. So actually, we can see a very weak stray field on the bilayer with high sensitivity measurements down to 5 microtesla. So it's about a 5 microtesla stray field. So this is a 10 times higher sensitivity measurement than our when we image a large region. So this allows us to see antiferromagnetic domain walls. And what that's coming from is that actually when you make these 2D samples, the top and bottom surfaces are never perfectly compensated. So it is somewhat similar to the surface magnetization you see in bulk chromium oxide, but for these 2D van der Waals materials, it allows you to see where the domain walls are, and it allows you to use that slight bit of uncompensation to actually drive the domain walls as a function of a magnetic field. So it's being able to visualize these domains allowed us to see a lot of interesting intralayer exchange coupling effects, but I won't go into them due to time. So, but we can also do actually these magnetization measurements inside of 2D devices. So this is similar to a magnetic tunnel junction, but it's similar in sort of in the transport signature, but the mechanism of magnetoresistance is very different. So this is a new device we made called a space charge limited spin transistor, where actually you have to conduct electrons across the 2D magnet, where one of these contacts touches the top of the 2-layer and one touches the bottom of the 1-layer. Okay, so they're made to opposite sides of a 1-layer monolayer bilayer junction, and then you have to conduct through the 2D magnet rather than tunnel across. So in this case, we can measure the device conductance as a function of field, and then you see that the current jumps whenever the bilayer switches to a ferromagnetic state. So whenever it goes, whenever the layers are aligned, then you have hopping allowed between the layers, so the conductance goes up. But sometimes you see, sometimes you see a gradual antiferromagnetic to ferromagnetic transition, and sometimes you see a sharp one. So gradual meaning I see intermediate levels of the conductance. We can just go ahead and map that as we take electrical measurements, and then we see that actually when you have a gradual transition, there is a domain wall sliding across the bilayer. And then when you have a sharp transition, for example, 4, 5, 6 on the way back, actually that is a coherent rotation of the magnetization of the top layer. So when the domain wall moves across the bilayer, actually it's in the bottom layer, which is shared by both regions. And when the magnetization actually switches at the top suddenly, it's actually just a flip of the top layer. So these type of this label of the states at all different values of the conductance is actually unique. We get that from NV center magnetic imaging. So you might say this is pretty self-explanatory, but there are actually signatures in the transport that's not that obvious. Okay, so actually we can take a look at the conductivity versus the gate voltage, and it just goes up. And then you might say that the only thing the gate voltage is doing is that it's adding free carriers to the channel. But actually, it's doing more than that, because I can actually sit at a single magnetic field and I can do the imaging. And by doing the imaging, I can isolate changes in the magnetic state as a function of the gate voltage. And what I see is that as I increase the gate voltage, the ferromagnetic domains start to slide across the bilayer. Okay, so this is another effect that increases the conductance. And what's happening here is that as you dope the sample, the interlayer exchange coupling changes to be less antiferromagnetic. So at finite field, it favors the ferromagnetic state. And this is partially reversible. As I decrease the gate voltage, the ferromagnetic regions now recede and move back. So these are things that you can do with NV centers that give you additional information that's not obvious to transport. Okay, so other examples of sort of imaging spin textures in real space include imaging the helicity of a domain wall. So whether the domain wall is block or nail, you can see that in the stray field, the quantitative stray field of the NV center. So block or nail just means whether the spin rotates in the plane of the domain wall. Nail means it rotates in the plane. Block means it rotates perpendicular to the plane of the domain wall. Right. So triple Q. So our spatial resolution is about 50 nanometers. So I think it's probably too triple Q might be too small. Yeah, but you can also look at skyrmion profiles and also look at the Moiré pattern, the Moiré unit cell in twisted chromium iodide, where you see patches of ferromagnetic regions and patches of antiferromagnetic regions. But there's some challenges towards this magnetization reconstruction. So in particular, actually, you can't tell the difference between sort of left block and right block. Actually, the component of the spin that's parallel to the domain wall, actually, we're not sensitive to that. And for the skyrmion reconstructions, they had to make some extra physical assumptions. Also, we integrate over the thickness of the sample, so it's not really layer resolved. And for Moiré physics, the spatial resolution is pushing what we can do. At the smallest twist angles, we can get maybe, people can get 100 nanometers, but for larger twist angles, the Moiré period is too small. Okay, so then we can also image 2D current flows, and this has been maybe perhaps the most fruitful for correlated physics. So for 2D current imaging, we try to invert the Biot-Savart law, and that's similarly done in reciprocal space. But in contrast to magnetic imaging of magnetizations for current flow, the reconstruction is one-to-one, completely unique. And that's because we have for 2D current flow, there's only two components. There's only two components, and then we also have the continuity equation, which constrains both component. So there's actually only one independent component. So 2D imaging is completely unique, and people have done really beautiful work imaging sort of hydrodynamic flows in both WTE2 and graphene at room temperature, where they see at the effects of viscous electron flow. So for example, when they make these little pockets or these pockets on the side of a graphene channel, you can see a counter-rotating whirlpool due to hydrodynamic effects, whereas if it was a purely diffusive transport, actually the whirlpool would be in the same direction as the current. So this has really revealed a lot about electron sort of scattering in these devices. So by imaging the stray field, you get the vector current profile. Okay, and the other thing about current imaging is that you can use what's called AC sensing sequences. So these sequences actually use so-called Hahn echo or dynamical decoupling techniques, where you're actually measuring the precession of the NV center. You're measuring the precession of the NV center on the equator. Okay, so what you do is you put the NV center on the equator with a pi/2 pulse. You let it precess, so it's going to go red, and then you flip it around the x-axis, and then you let it precess again. So if you actually had a static magnetic field, you see that actually the precession angle at the end of the Hahn echo is 0. Okay, so the work that you did in the first half of the precession got negated. You got essentially negated, and then you catch back up in the second half. However, if you can, so that's 0. However, if you can control your signal, so controlling your signal by changing the sign of the current, or maybe inducing an AC magnetic oscillation, then you can rectify that signal. Essentially, the phase that you get is the modulation function, which switches sign at every pi pulse, multiplied by the magnetic field. So if the magnetic field also switches sign, then you can measure a non-zero phase. And this is beneficial because it actually reduces noise. So it reduces noise and extends the coherence time of the NV center. So that was an example with just one pi pulse, but actually what you want to do is you want to put even more pi pulses. So if you put more pi pulses, the frequency that you're sensitive to actually gets more and more narrow. Okay, it gets more narrow at the frequency where you essentially switch sign at every pi pulse, and then you're rejecting more and more noise and isolating your target signal. So this is exactly the same as classical lock-in techniques, except for the quantum system, it has to be completed within the coherence time of the NV center. So with that, the more pi pulses you put into your sequence, the longer is the coherence time, reaching actually 1 second for the NV center at low temperature for 10,000 pulses. And this coherence time directly goes into your sensitivity of the magnetic field. So with these pi pulse sequences, you can reach sub 100 nanotesla per root hertz sensitivity for AC magnetic fields. So this has to be an AC magnetic field. So actually, we wanted to use these techniques to we were interested in photocurrents in Wall semimetals. So there was a lot of work, maybe 3 or 4 years ago on these transition metal ditellurides, saying that an enhanced photocurrent was observed due to several effects. So why were people looking in these transition metal ditellurides? Well, it is related to the physics that Joel Moore was talking about, in that actually these materials have Weil points, actually type 2 Weil points, and they break inversion symmetry. So they should be host to actually a nonlinear photogalvanic current that's related, moreover, to the topology of the Weil points. In particular, Weil points have divergent Berry curvature, so you might think that they would have a particularly large response for this nonlinear photocurrent. So actually, but the problem was actually the photocurrents that people were measuring were actually in the AB plane for light that was nominally normal incidence. So because I have these two mirror planes in the AB plane, actually I shouldn't get nonlinear photocurrents if I just have normal incidence, normal incidence. And that's because, and that's because actually the nonlinear susceptibility tensors there, they're non-zero only if you break certain symmetries. So for these Wall semi-metal transition metal ditellurides, the only ones that are possibly non-zero involve the C-axis. So you either have to either the light has a component along the C-axis, or the current is along the C-axis. So all of these papers actually, they assume something slightly more complex to justify why they had the photocurrent. For example, a third order effect, or maybe your light is slightly oblique and you have a tip, so you get some Z magnetic field, or due to gradients in the optical power, or you had edges. So it's not the most satisfying. Is there something else going on? So we try to look at the flow of these photocurrents with NV center magnetometry. Okay, so in particular here we have an ensemble imaging chip where there's NV centers everywhere. We shine light through the diamond membrane. So the diamond membrane is very thin. and our light comes in from below. So we shine light through the diamond membrane on the WTE2 sample to excite photocurrents, and then we raster the NV center readout beam relative to the photo excitation. So then we can map the straight field relative to the photo excitation, which gives the phase precession there is directly proportional to the straight field of the photocurrent, and then we can apply the current reconstruction method that I introduced. The other thing to note here is I do a optical chopping technique in conjunction with this dynamical decoupling sequence on the NV center to get very high sensitivity readout of the photocurrent. Okay, so actually I see this very surprising pattern that switches sign actually 4 times. So what does that look like? So actually, if I invert Biot-Savart law, I can get the current flow. And actually, you can convince yourself that actually it has to be 4 vortices, where the blue color is blue color is just currents flowing in towards the center of the photo excitation, and red is flowing out. So what we see is that actually the photocurrent flows out along the B-axis and in along the A-axis. So is that a fluke? Just for this one sample, well, I can rotate the sample and map the photocurrent again, and then the pattern of straight field I get rotates, and it again indicates that the local photocurrent is circulating in the manner that's aligned with the crystal axes. So how do I understand that? We work with Professor Ying Ran at Boston College, where we can understand this due to an anisotropic photothermoelectric effect. So it's actually not due to any nonlinear susceptibility, it's due to actually laser-induced heat. But it's an interesting effect because actually the laser-induced temperature rise induces a gradient that drives currents due to the Seebeck effect. But here we have anisotropy where the Seebeck coefficient along the A-axis is actually more negative than the B-axis. So actually what that means is that more electrons are going to come out along the A-axis than on the B-axis. This induces a pileup of electrons, more pileup of electrons along the A-axis than the B-axis, which induces a long-range electrochemical potential that tends to circulate the electrons from the A-axis to the B-axis. So actually, if you had isotropic thermoelectric coefficients, actually the long-range electrochemical potential can exactly cancel the Seebeck potential, and then you get no photocurrents if it was isotropic. But if it's anisotropic, actually this leads to actually circulation of currents rather than the current stopping. And then we can simulate this. We can simulate this model using conductivity parameters for WTE2, and it very much agrees with the experiment. And we can also look at tantalum iridium tellurium-4, which has more anisotropic conductivity, and it matches our data almost really well. So then you can go to DFT calculations, and you see indeed actually DFT calculations predict that the Seebeck coefficients should be different along the 2 axes. And this is due to the fact that these are type 2 Wall semimetals. So you have both electron and hole bands, which can give you different signs of this Seebeck coefficient depending on their band velocity in the different directions. So this actually, by understanding the local photocurrent mechanism, I can actually show how to design devices to extract that photocurrent. So that's given by in metals, that's given by the Shockley-Rommel theory, which says it's an interaction between the local photocurrent and essentially your electrostatic streamlines, electrostatic potential inside the device. So even though the anisotropic photothermoelectric effect has pretty high symmetry, by engineering actually asymmetry in my device, so these oblique edges, as well as contact placements that are slightly asymmetric, we can actually immediately understand the entire photocurrent collected over the entire device. So this is a nice example how quantum sensing was able to actually solve a mystery that global transport measurements could not. I mean, at least give more to the story than global transport measurements indicated. Okay, so the other big area of quantum sensing is what's called noise spectroscopy. So there you're measuring fluctuating magnetic fields instead of DC magnetic fields. So in this case, one of the things that people can do is to measure relaxometry. Relaxometry, which is the decay of an initially polarized spin. So for example, if you initialize in 0, after some time, it will go to the opposite state. Okay. And what that is due to is actually it's due to the noise power at the frequency of your transition. Okay, so that's due to essentially the autocorrelation of the magnetic field, the Fourier transform of the autocorrelation of the magnetic field, which is actually related to the spin-spin autocorrelation. So essentially, you can relate the fluctuations of the magnetic field to the spin fluctuations in your material, which actually could tell you. So actually, theorists like this a lot. So the spin correlations actually tell you a lot about the interactions between the spins. This can also be current fluctuations as well. So with this technique, we can tell if the underlying spin excitations are broad or sharp in energy and what their spatial correlations are. So here you see an example from Chenghui Du's time in Amir Yacobi's group, where you can see actually the m sub s equals 0 in purple. After I polarize in that state decays into the m sub s equals +1, but not really into the m sub s equals -1. And that's due to the fact that actually the m sub s equals -1 is below the Magnon band gap at this magnetic field. This was at a particular magnetic field. So m sub s +1 was above the band gap. M sub s equals -1 was below the band gap. Yep.
Actually separate the spin out from the Maclaurin effect on impurities?
Yeah, I'll get to that. So it's very nuanced. So it's going to be nuanced. So this effect also happens not only in the depolarization but also in dephasing. So whereas the T1 relaxometry we were sensitive to noise at gigahertz frequencies due to the energy separation between the m sub s equals ±1 and 0 states. So for this effect, we're measuring dephasing. We actually can tune what frequency we are sensitive to by changing the delay between our pi pulses. So so the filter function I was talking about, you can actually deliberately change where that filter function is centered by the spacing of your pi pulses. And because each pi pulse is around 10 nanoseconds, that means we're really accessing dynamics at noise dynamics at kilohertz to megahertz frequencies. So you can see we're just measuring the decay envelope of the coherence of the NV center. So yeah, so people have used this for a variety of effects, including measuring the electron phonon Cherenkov effect in ultra clean graphene, where they see the noise actually gets greater as you get farther and farther from the contact. And that's just due to the fact that actually the electron drift velocity in these ultra clean devices are faster than the acoustic phonon velocities. So you get sort of a sonic boom of phonons where it sort of builds up along the direction of the current. You can actually look at noise in antiferromagnetic domain walls. So although you might not be able to see antiferromagnetic domain walls in the stray field signature, their noise might help you identify them. So if you're over a domain wall, there's going to be more noise than if you're in a if you're in a saturated state, as well as people have looked at noise due to vortex motion, so current oscillations in superconductors. So to your question about whether you can see difference between spin-ons and magnons and sort of different phases of magnets, the answer is maybe. So there's a lot of theory proposals out of the Demler group and elsewhere where they make predictions about the noise spectrum as a function of temperature, as a function make predictions about the noise spectrum as a function of different different materials. So maybe vortex, anti-vortex, and binding in the BKT transition, maybe Wigner crystals, and also time reversal symmetry in superconductors, where essentially actually the transitions between spins, they require sort of circularly polarized noise in principle. But these experiments are very challenging because it's actually so every time, you know, the noise here, if it goes from 10 to the -3 to 10 to the -6, then I have to, it's basically all zero in the experiment. If I really want to tell the difference between 10 to the -3, 10 to the -6, my experiment has to get 1,000 times actually longer. And there's other sources of decoherence that these models don't consider, which might be convolved. But you know, it's a worthwhile effort to try to look for these things. So you basically have to vary the temperature, you know, vary the distance of the tip from the surface, which gets you access to different length scales, and maybe vary the energy of your that energy of the noise that you're sensitive to. That means changing the magnetic field. Okay, and also NV center is considered a non-invasive technique, but is always considered a non-invasive technique in theory, but that's not always true. So actually we tried motivated by these theories, we tried to look at noise in few layer chromium chloride, which is a model system for the 2D XY model. So the 2D XY model should have vortex, anti-vortex, should have a BKT transition with magnetic vortices and magnetic anti-vortices. So we tried to do the T2 noise relaxometry on these samples, and actually, what you expect to see actually is the X projection of the phase get diminished, right? So every experimental run, the precession is random. So X, if you average X, it should get sort of shorter if you prepare the X state in the beginning. But and that's what we see. So on a region of the sample with just no sample, X is decaying. But on the 5-layer region of chromium chloride, X is decaying very quickly. But what you don't expect is there to be a preferential actually Y projection. Actually, on the five layer sample, you see that Y actually goes up. Whereas if it was pure decoherence, Y should stay at 0. So actually, this is not actually pure decoherence. Actually, we're getting a coherent precession on top of the flake. So there's actually some transient magnetic field that's synchronized to the laser pulse. So the first laser pulse that I used to initialize the NV center spin actually creates a transient magnetic field. So we got sidetracked by this, and then we sort of spent too much time studying this and ended up writing a paper. So instead of using the green laser pulse, we put in another laser color where we can vary the wavelength, and we can then do the same thing as our photocurrent. We can scan the green laser beam as a function of the pump beam relative to the pump beam, so we can map the spatial profile of the transient stray magnetic field. So we can actually increase this delay, and what you see is actually the transient stray magnetic field diminishes, and because of this transient pattern allows us to say that it's actually an increase in the magnetization, not a decrease. Okay, so one very trivial explanation would be that just the laser heats up the magnetic sample and reduces the magnetization for a little bit just by temperature. But actually, because we map actually exactly what the dipole field is, and we can also map the DC field, we know that it's actually an increase, not a decrease. And it has very long lifetime, 26 microseconds, which is longer than the exciton lifetime. So it sort of suggests to us actually charge dynamics. So actually the explanation is not all that interesting. It's due to defects in the band gap. So we can prepare a sample where we look at the transient stray field and correlate it to the photoluminescence. So in this sample, we cover half of the sample, and we see that actually when we see strong transient fields, actually we see very low photoluminescence from the chrome chloride. So it suggests to us that actually non-radiative exciton recombination actually leads to this effect. So our proposal for this effect is that actually we have an Auger recombination of the excitons. So normally the excitons, it's an electron hole pair, they just recombine with each other and give off a photon. But if you have a defect state within the band gap, that energy can actually be given off to the defect state, promoting the defect state to the conduction band, which in this material is spin polarized. So actually that can lead to actually optical doping of the material, which leads to actually an enhanced magnetic field magnetization. So we work with DFT group led by Professor Binghai Yan, and then they basically said that actually indeed hydrogen bonded H2O on the surface of this material could provide the right basically unpolarized defect states within the band gap. And when non-radiative exciton recombination happens, these unpolarized defect electrons become polarized. So maybe not very interesting, but actually the technique is actually very interesting for measuring optically induced magnetic fields, including optically induced, say, Meissner effect or otherwise. And one last thing we did is that actually instead of measuring the spectrum of the noise through relaxation, could you actually measure the susceptibility directly? So those are related by the fluctuation dissipation theorem, where it says the spectrum of the noise is related to the imaginary part of the susceptibility. So to measure the susceptibility of the magnetization, we have to drive it with an AC magnetic field. So we can just put in an extra coil here, similar to just your normal squid, NPMS squid AC susceptibility technique. You just have a coil that drives a global field. It's going to induce a AC magnetization change, and then we're going to try to pick up the AC magnetic field through one of these quantum lock-in sequences, where if we time where we put the pi pulses in synchrony with the AC excitation, we measure the AC excitation and the real part of the sample response added together. And if they were ideally 90 degrees out of phase, we can measure the imaginary part of the AC magnetic response. So it turns out actually, so there's some hierarchy of sizes of these fields. So the coil field is actually much bigger than the real part of the sample field, which is much bigger than the imaginary part. So actually it's pretty tricky to get out the imaginary part. So this is solved in classical squid measurements by doing the 2 counterwound loops. We can't do that here. So actually in this first experiment, we actually only measured the real part of the AC response. So we basically attributed all of the signal AC amplitude that we got to the real part. And then we can measure how much the coil produces by going above TC or going away from the flake. So here's a 2D ferromagnet chromium bromide. We can measure the AC susceptibility in a 10-layer thick chromium bromide. And that was actually limited not by our NV sensitivity, but was limited by sort of our exfoliation techniques at the time. So this is actually the first paper out of my group, but it's still pretty good. So this 10-layer flake has very tiny moment, 10 to the minus 10 EMU, just based on the size. We can measure the DC excitation, DC magnetization, and we can measure its AC susceptibility as we cool down in temperature across TC. So we can measure it for different values of the field cooling field, sort of the amplitude of the cooling field. So we're cooling it in a different field, and then you can see that we can do DC at the same time as AC. You see at the lowest field, the DC magnetization is barely rising. It means that it's actually forming a lot of small domains in the sample. Whereas at high field cooling, we see a strong rise in the DC field. So it's actually becoming saturated and forming only a single domain. In the case where we have small domains, we have first the initial paramagnetic to ferromagnetic transition, which that coherent AC rotation is first picked up given by a given by a critical exponent, which we find to be around 1, same as mean field. And then below TC, we have basically essentially domain wall motion. So domains getting bigger as a function, bigger or smaller as a function of the AC field. But even so actually in the strong field cooling case, because we have a very point sensor, we can be actually sensitive to just actually a single domain wall. So actually, if a single domain wall pins and then depins as a function of temperature, we can get kinks that you see for a non-monotonic behavior that's sensed by the NV center. So this is a very different regime than your squid NPMS, where you assume your sample to be a point source. Here, actually, the detector is a point source, and the sample is actually an infinite plane, right? So so that's all to say that actually, if you measure at different points, measure with different NV centers at different points, you might get something different for this sample. Okay, but that's not bad for first attempt to measure the susceptibility directly. And for these very small samples, there's only a couple techniques that can measure the AC susceptibility, AC moke and AC squid. Okay, so my conclusion is that, yeah, I hope I convinced you that quantum sensing is emerging as a good tool, a promising tool for condensed matter physics and hopefully correlation physics in the future. So I hope you understood how we can image magnetic textures, or understood a little bit more how we can image magnetic textures, current flow, and their excitations in 2D materials. And then I think there's a lot of fruitful avenues for collaboration and overlap where we can do combined magnetic and electric sensing, or combined magnetic and temperature sensing, as well as going to high fields to image current flow in quantum Hall states. And then there's even possibilities to measure noise correlations in space. This is a work from Natalie de Leon's group at Princeton, where they can simultaneously measure 2 NV centers and measure the correlations of the magnetic fields at 2 different points in space. So with that, I'd like to thank my lab. So the graduate students in my lab, some of them have graduated, 2 of them are graduate. Yushen and Xingyue have graduated. And then I'd like to thank my collaborators, and some of the papers I've talked about are referenced here. Thank you very much.
Thank you for the nice talk. Okay.
Hi, Professor. Thanks for your talk. And I have some questions. In here, you use the NV center as a tip to scanning the mechanism. Why do you use the NV center, not other technology like QSM that use a Kerr effect to measure the magnetic field?
So QSM means what does it stand for?
Actually,
quantum twisting microscope.
I think there is other magnetometer that is
Right. Okay.
Yeah.
Squid on a tip. Yeah, that's a great question. Okay, so squid on a tip has a much higher sensitivity than the NV center, but the distance away from the sample is a little bit larger. But in general, they are more sensitive than the NV center, but they must operate at much lower temperatures, because this is it's essentially a Josephson junction. So they can only operate at lower temperatures, and their sensitivity actually changes as a function of magnetic field. So I would say just the NV center is a little bit more versatile. So we can scan samples. We're not afraid to sort of really touch on the sample, and potentially we can get closer. So the ultimate limit of how close an NV center can get to the sample has not been reached yet. So that could be as close as sub 10 nanometers. Whereas squid on a tip, I believe if they touch the sample, that causes some damage to the tip. So
what about the
MFM?
QSM using magneto-optical curve effect imaging.
Oh, magneto-optical curve effect is limited by optical spatial resolution. So that is like 300 nanometer spatial resolution, whereas NV Center has much higher spatial resolution, so sub 50 nanometers.
And will the pump rate and the probe rate will change the property of the sample?
Will the optical
Yeah.
excitation?
Yeah.
So usually you have to check that. So you usually not. Usually not. Actually, on these tips, you can use much lower optical power because of just focusing and waveguiding effects. So you do have to check that. But usually for samples that have high TC, high Curie temperature is not such a big deal.
Okay, thank you.
Yeah.
Yeah, thank you for the nice talk. So I have a question about the noise spectroscopy.
Mhm.
So I'm trying to understand the origin of these electromagnetic fluctuations. So how do I understand these fluctuations?
Okay. So it's temperature. Usually it's temperature. So in equilibrium, it's basically temperature. So you're not at zero temperature. So any magnon mode will be semi occupied, and then for superconductors, you're going to have quasi particles. So it's just thermal equilibrium. The occupation of the lowest energy states with lowest energy excited states at thermal equilibrium.
Okay, so
You can also drive it directly. So for magnons, you can apply a microwave to drive it.
okay, so that does that mean if the temperature is small enough, I cannot basically observe
Yes.
any pronounced?
Yes, that's actually exactly what you see here. So in this plot, as T goes to much smaller than TBKT, the noise is going down.
Okay,
Right? That's exactly what you see. Yeah.
thanks.
Does that have any sort of potential into resolution? Or what is expected?
Oh yeah, it has great energy resolution actually. So for T1 relaxometry, it's basically you have to be resonant with the NV center transition. So the energy resolution is basically the line width of the NV center, which is like a few megahertz. So a few megahertz probably is like a delta function. It's a delta function in energy resolution, essentially. Yeah, question. Yeah.
I need to say out loud, I guess. Sorry if I missed it, but like
Yeah.
what fundamentally limits the spatial resolution of the technique? Is it
Right.
how close you can get the NV center?
Right. So that's exactly right. So it's just how close you can get the NV center, and then you can't create these NV centers exactly at the surface of diamond. So if you create them exactly at the surface of diamond has a reconstructed surface with dangling bonds, and that's going to decohere the NV center very quickly. But actually it's the when you do these scanning measurements, it's actually even farther than how deep it's implanted into the diamond, and that's usually due to actually just AFM conditions. So depending on how you feedback, whether you amplitude feedback or frequency feedback to stabilize your AFM set point, you can get closer to certain samples.
Yes, with the ultimate technique may become someday.
Yeah, I think people at room temperature have shown less than 25 nanometers from Christian Degen's group, but I think it's going to be hard. But one thing is these van der Waals defects, where van der Waals interfaces between two van der Waals materials are actually you can get much closer. Like in the quantum twisting microscope, actually, it's nanometer, sub 10 nanometer sort of displacements.
Okay, due to time limit, let's thank the speaker again.